Welcome back. We're going to look at section 4.2 and build a little bit of a supplement to it from the notes that we had on the previous video. Starting out, this is something that was not really stressed or really presented in the notes, but there are two types of probability. We're actually using theoretical probability right now when we use the addition rule for disjoint or mutually exclusive events. Anyway, theoretical probability is just calculating probability values through formulas and things of that nature. Empirical probability, these are probability values arrived at through observation or simulation, and we've done this. We've rolled die, we've built tables with outcomes, we've run simulations, and we've gotten estimates of true probability values this way. So those are two things. I doubt you'll see this on a test or a quiz or anything like that, but just so that you know, there are two types of probability. Now, one thing that we need, since we are using definitions for probability like success over total and things like that, we really need to figure out the total number of outcomes. Well, an outcome is one of the possible things that can occur as the result of an experiment. If I flip two coins, I can get two heads. That's an outcome. I could get one head, one tail. That's another outcome. What we want to do is be able to list all of those outcomes so that they're complete, so that we have every possible outcome that can occur, which will create the sample space. And the sample space is the set of all possible outcomes. So if we flip one coin, there are only two things that can happen. You can get a head or you can get a tail. That's it. But if you flip two coins, you can get two heads. You can get one of each in two different orders. You can get two tails. So the first one is like 2 to the first. The second one is like 2 squared. So if you look at flipping 3 coins, yes, that would be 2 to the third, which is not 6, it's 8. And there are all of the possible outcomes that you can get. We can use a table to help us. We can use trees to help us. So let's look at some of those things. So here's a tree diagram. You're going to actually learn tree diagrams later in a different kind of way. But if we just need to figure out the number of outcomes, and it's with more than two things like flipping 2 coins, if we flip 3 coins, this might be a good way to figure out the way that these can all occur. So the first coin would be a head or a tail. So let's say you get a head. When you flip the second coin, it could be a head or a tail. And let's just say you get a head on the second coin. If you flip a third coin, you can get a head or a tail off of it. So you've created this branch. Head, 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 there it is. Head, head, tail, there it is. Head, tail, head, there it is, and so forth. And that's going to be 3, 2, 4, 6, 7, 8 outcomes. You can also list or state sample spaces in words. You could also truncate them if it's very, very long and it just takes forever to write. So if we go back, you could theoretically say the sample space for flipping 3 coins is head, 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 comma, tail, 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 comma, dot, 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 comma, tail, tail, tail. So long as you can establish a pattern that people can recognize, that can spare you from having to write all of the particular outcomes in the sample space. Okay, we did tables. On the one with the banana, who can win the last banana, was a dice rolling game for people stranded on a desert island. We filled in a table just like this one. So here are all the outcomes for one die. Here's all the outcomes for a second one. If you roll them together, you could get a 1 and a 1. You could get a 3 and a 4, or a 6 and a 4. We just listed all of them. We ended up with 36. So when we wanted to say, what is the probability of rolling at least 1 4? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 ways that that can happen out of 36. There's your probability. So tables, very helpful. All right, we've had a lot of definitions for what probability is. It's the proportion of desired outcomes you would see in a very long series of trials. We can also say that it's success over total. Here it's the, let's say the probability of A is the number of elements in A divided by all of the elements in the sample space. Okay, so A is, if you see it as a success, and the total would be everything in the sample space, so success over total. So basic rules for probability. 2 requirements for a probability. Probability is a number between 0 and 1. And I think I stated this pretty firmly in class. 0, if an outcome has a 0 probability of happening, that means it can't happen. It's certain to not happen. It's impossible. If an event has a probability of happening equal to 1, that means it's certain to happen. It's going to happen. Anything in between is, well, it could happen, maybe it didn't happen, but you cannot have a probability that's negative because you can't go below impossible. You cannot have a probability of, say, 1.2 because you can't have a probability that's more than certain. Certain is as far as it gets. So for any event, your probability will be some number between 0 and 1 inclusive, which is right here. We have a probability assignment rule. I don't think you'll have to memorize it as such, but the probability of the set of all possible outcomes of a trial must be 1. If I were to list the probabilities for flipping 3 coins, all of those 8 outcomes, all of the numerical values for them would have to add up to 1 because that is the sample space. It's everything that can happen. Therefore, the probability of the sample space is 1 because it represents all of the possible outcomes. We can use Venn diagrams to represent probabilities, and here is just the most basic it can get. It's a rectangle with an S in it, which represents the sample space. Everything that can happen. We haven't really dived into the sample space to create separate events or anything. It's just, here's the sample space. It encompasses everything that can happen. We also covered the complement rule. The set of outcomes that are not in event A is called the complement of A, and it's denoted A with that little superscript C. So when you see A, that represents whatever event you've defined A to be. If you see A with that little superscript C, that's events that are not in A. Probability of an event occurring is 1 minus the probability that it doesn't occur. Think about it. Either A happens or it doesn't. There are no other options. Either it happened or it didn't. So the two together have to add up to 1, which is shown right down here. So they add up to 1, which is the sample space. You can rearrange that. You could subtract the probability of A complement from both sides so that the probability of A is 1 minus the probability of its complement. So if you know one of these, you automatically know the other of them. Here is a Venn diagram of A and its complement. That's the sample space, so that's all that can happen. So here are where your event of interest A is occurring, and everything outside of that is where it's not occurring. So your complement rule, you can think back to class notes. How prevalent was high cholesterol? Remember, high cholesterol, the probability was given as 0.16. The probability of borderline was 0.29. So if we pick a person at random, the probability of them either having a high or borderline high cholesterol, which is kind of a problem. So the probability of having somebody with a cholesterol problem is the sum of those two probabilities, because high and borderline cannot happen at the same time. So this is your addition rule for mutually exclusive events. We're jumping the gun a little bit, but the probability is just the sum, which is 0.45. There is only one other thing that you could get when you select a person at random, and that would be that the person has normal cholesterol, which is anything, below 200? Okay, well, if you know what it is to have a problem person with cholesterol, which is a probability of 0.45, then normal would just be 1 minus that, because that's the only other outcome that's left. So all three of them have to add up to 1. If you know the two, add them up, subtract them from 1, and there's your complement rule. Now there's this phrase that you can see in some of your probability questions, which I've put in red, which is at least 1. That's the at least 1 rule. So here is a great reason why your complement rule would fit something like this so well and save you so much work. What is the probability of having at least one boy out of 4 children? Okay, would you rather just figure out all the individual probabilities? Here's a boy on the first, or the second, or the third, or the fourth, or 2 first and second, and then 2 girls, and then first and third, first and fourth, or third and fourth, or second and fourth, or third and fourth, or 3 boys. You see what's happening here. There's so much you have to calculate, and we don't even know how to do a problem like this because we know the or means to add, but what about the boy and boy and boy and girl? And means to multiply. That's the the multiplication rule, and we haven't even covered that. So this is just crazy mix of addition and multiplication and a lot of margin for error. Or how about the probability of at least 1 equals 1 minus the probability of none? Wouldn't that do it? Because if we did 1 minus the probability that all you have is girls, then it would be your answer would be the combination of all of these things, because you would have at least one boy as the events that were left over. Okay, so 1 minus the probability of no boys is going to equal the probability of at least 1. So it's a really powerful way to use the complement rule. All right, so this is now the addition rule for mutually exclusive events. And these are events that have no outcomes in common, thus they cannot occur together. And in a Venn diagram, you see event A and event B don't cross each other. They don't overlap. They're separate. So they're mutually exclusive. Another way to say mutually exclusive is disjoint, but I don't know that this is going to come up in our vocabulary. If it ever does, it means mutually exclusive, but there you go. So if you have 2 events that are like that, they will be A or B. Probability of A or B. Or means addition in the language of probability, and means multiply, which we will see later on. So you can write the probability of A or B with this kind of set notation. We covered this a little bit in class. This symbol means or. It also means union. It's just a set symbol that means or. So you can write it either way. So the addition rule for mutually exclusive events, for 2 disjoint or mutually exclusive events, A and B, the probability that one or the other occurs is the sum of the probabilities of the 2 events. So here it is in the fancy notation. This means or, and you just figure out the answer by adding the 2 probabilities together. So if I flip one coin, probability of a head is 0.5, probabilities of a tail is 0.5. When you flip that coin, you can't get both. You get one or the other. See the or? So for the head, the probability is 0.5. For the tail is 0.5. For A or B, head or tail, you just add them together and you get 1, which makes sense because when you flip a coin, you can't get anything else but a head or a tail. And no, don't think, well, it could land on its side. This is not the Twilight Zone. So this is the formula for the addition rule, so long as A and B are mutually exclusive. If they're not, we will have to do one other little step to make that work. So here's just addition rule for mutually exclusive events. Now we're going to assume that never married or divorced, well, I guess those things would be mutually exclusive. Some people will argue that you can be married and divorced at the same time, but let's just assume all of these are mutually exclusive. So for women aged 25 to 29, here's the 4 things they can be for marital status. And so each of these numbers added up have to add to 1 because there are no other options. So the probability of never married or divorced, since they're mutually exclusive, is going to be the sum of the 2 probabilities, which is going to be this 0.353 plus this 0.071. And there's your answer. So I hear the lawn people in the distance and they're noisy, so they're just going to interfere moving forward. So it's time to quit. I will see you next time. I appreciate that you took the time to watch.